So we were last focusing on nomenclature for transition metal containing compounds. The unique quirk about transition metals is that they have variable charges. As a result, the charge of the transition metal needs to be specified using a Roman numeral. So let's try, as an elaboration on our previous examples where we named a series of transition metal containing compounds, let's now try to write the formula from the following compound names. So we have scandium hydrogen chromate. Scandium is Sc. We know that the charge is given in the Roman numeral as 3+. And then hydrogen chromate. So chromate is CrO4 2-. And if we add a H plus to get our hydrogen containing polyatomic ion, hydrogen chromate would have a charge of -1. We cross our charges, and that in turn gives us as a formula scandium HCrO4 3. So this is the formula for scandium hydrogen chromate. What I would like you to do now is to work on the next two examples in this series. Let's take about 3 to 4 minutes to work on these examples, and I'd like you now to try and write a valid formula for each of these two compounds. Remember, you need to figure out the charge and formula of each of your ions, and then by crossing the charges, you can get the formula and subscripts for your neutral ionic compound. So let's spend about 3 to 4 minutes on these two examples, and I'd like to see some responses in the chat or verbally with proposed names for these two compounds. And we're starting to see a pool of responses in the chat. Let's try to get a few more responses, and let's keep working on these examples. And don't be shy to contribute your response, even if it necessarily doesn't match your classmates' responses. So we're starting to see a reasonable pool of responses. Let's keep working on this example, and we'll discuss in about another 2.5 minutes. Let's try to get a few more responses in the chat. And one thing that you just want to make sure is just double check your charge assignments. Seems everyone's being quite careful in assigning the correct charges, even for the hydrogen containing polyatomic ions, which is always good to see. And we'll discuss this example in about another minute to a minute and a half. Okay, so let's discuss this example. So for cobalt-2 hydrogen phosphate, cobalt is CO, our charge is 2 plus, phosphate is PO4 3 minus, hydrogen phosphate is HPO4 2 minus. We cross our charges, that gives you CO2 HPO4 2, and then we remember we can simplify our ratio of ions, and we want the simplest ratio of ions. So that simplifies to the following formula. Does that make sense? Perfect. So for iron 3 bromite, iron 3 is Fe3 plus, bromite is BrO2 minus. We cross our charges, and that gives us Fe BrO2 3. Do these examples make sense to everyone? I find transition metal containing compounds are easier to write the formula for than even normal compounds because the name tells you the charge. Any questions on this example?
I have a question when it comes to like for instance the cobalt-2 example.
Mhm.
Like I put a parentheses even though I didn't need to like add more of the elements.
Yeah, that
Like
would be
is that
fine.
okay?
That would be
Okay,
fine. Yeah.
thank you.
As long as you have the correct number of each ion. The reason why I omitted a parentheses, if there's just one, then the parentheses isn't necessarily serving a function. So I usually like to get rid of it for clarity. If you find it's easier to keep track and make sure that you're counting the correct number of ions, you can certainly place that in parentheses, and I would understand the meaning that you're trying to convey.
Okay, cool. Thank you.
So let's work on the next set of examples. So I'd like you to provide a formula for the following compound names. And let's work on these 3 examples, and let's spend about 4 minutes on these 3 examples. And don't be shy to propose the name for each of these. Oh, sorry, propose the formula for each of these compounds given the name. So we'll work on these examples just as a follow-up now that we've seen some representative examples and we've had the opportunity to discuss problem solving for these types of problems. Let's now try to apply what we've learned to a new set of examples. And if there are any questions as you work through these examples, don't be shy to ask them in the chat or verbally.
When it ends in "ide," is that just a negative? I can't remember.
So atomic anions end in IDE, but there are also some polyatomic ions that end in IDE. And if you're unsure, you can check the polyatomic ion table.
Oh, okay, got it.
Does
Thank
that
you.
make sense?
Yes.
So in general, the IDE ending is indicative of an atomic ion in 99% of the cases, but there are some polyatomic ions with an IDE ending of their name. So let's keep working through this example. We're starting to see a reasonable pool of responses in the chat. Let's try to get a few more responses before we discuss this example in about another 2.5 minutes. And we're starting to see more proposed responses in the chat. And I greatly appreciate that everyone is assigning their subscripts for polyatomic ions using parentheses. We'll keep working through this example and we'll discuss in about another minute. And it's great to see this level of participation so far in our class problem solving sessions. And if there are any questions as you work through these examples, don't be shy to ask it verbally or in the chat. Okay, so let's talk about this example. Vanadium 5 oxide. So we have vanadium with a 5 plus charge. Oxide is a derivative of the oxygen anion as a group 6A element. Oxygen forms an anion with a 2 minus charge. Now that we have our two ions, we cross our charges, and that in turn gives us the formula. Does this make sense to everyone? Let's look at this next example. We have titanium 4 hydroxide. So we have titanium with a 4 plus charge. Hydroxide, what's the formula of hydroxide? Just to make sure we're all on the same page. OH minus, exactly right. So now that we have each of our formulas and charges, we cross our charges. And that in turn gives us the formula for titanium hydroxide. Does this example make sense to everyone? Let's keep going now. iridium 2 iodite, so iridium is IR, has a charge of 2 plus. Iodite is IO2 minus. Now, all we have to do is cross our charges, and that gives us IR, IO2, 2. There we go. Does this example make sense to everyone? Is everyone comfortable with writing the formulas from the name? If we don't have any other questions on this example, let's keep moving on and let's talk about hydrates. So what is a hydrate? Hydrate is a molecule consisting of an ionic compound, otherwise known as a salt. And critically, as the name implies, hydrate from the prefix hydro has associated water molecules. A close relative of the hydrate is what's known as the anhydrous compound. It's a hydrate without any of the associated water molecules. So for example, if our hydrate was like cobalt chloride hexahydrate, the anhydrous sample would just be cobalt chloride. Now, note the hydrate and anhydrous sample are different chemical compounds. It's not just a wet salt. It's an entirely distinct chemical species. Thankfully, naming hydrates is pretty straightforward. First, you write the name of the ionic compound. So you have to remember your rules for naming ionic compounds and determining whether it's a transition metal or a main group containing ionic compound. Once we have that out of the way, you write the prefix for the number of water molecules. And these prefixes are found below. Don't worry, even though it seems like a lot to memorize initially, you'll use these prefixes again when you're naming covalent compounds. So it's not like you're only memorizing it for one purpose. Finally, once you've included the prefix for the number of water molecules, you write hydrate at the end of the name. So just to show everyone how this works out in practice, first, if we look at the formula for cobalt chloride dot 6H2O or hexahydrate, we put a prefix of hexa because we have 6 water molecules. And then because we have associated water molecules as part of the chemical formula, we end the name with hydrate. So this would be cobalt 2 chloride hexahydrate. Does this make sense to everyone? Does this naming process make sense to everyone? Any questions so far that I can address? Okay, so let's focus on naming a few compounds. So I'll do the first one, you'll do the second one. So in this case, I note the number of associated water molecules. So naming my base ionic compound, if I think about copper sulfate, I know that sulfate has a 2- charge. And as a result, copper, in order for our charges to cancel, will have a 2+ charge. So I'd name my base anhydrous compound as copper 2 sulfate. And then since I have 5 water molecules, I use the prefix of penta, and then I conclude the name by writing out hydrate. So this would be the full name for the following compound. Does that make sense to everyone? So let's try to apply what we've learned and write out the formula for the following compound. And let's spend about 2 minutes on this example. And let's try to get a few more responses in the chat before we discuss. And make sure you have the correct prefix if we just have one water molecule. Yep, perfect, perfect. It's good to see the revised responses after double checking the prefix in front of the water molecule. Okay, so let's name this compound. So first we name our anhydrous species. So we have lithium hydrogen sulfate. We have one water molecule, so it would be monohydrate. Does this example make sense? Yes, you do have to put monohydrate because it indicates the exact number of associated water molecules.
What does the little asterisk mark mean?
It just means that we have associated water molecules. It's also written like this, where there's a dot, and that's what you'll often see in your textbook.
Oh, okay. Thank you.
Any other questions? So let's now try another variant of this problem, and let's work on writing the formula for the following compound. So we have nickel 2 carbonate tetrahydrate. So let's spend about 2 or 3 minutes and let's try to write a valid formula given the following name. And let's try to get a few proposed responses in the chat. And we'll discuss this example in about 2 minutes. And it's nice to see a reasonable pool of responses in the chat. And then we'll discuss this example in about another minute. Okay, so let's discuss this example. For nickel 2 carbonate, we have nickel 2 plus, CO3 2 minus. We cross our charges, and that in turn gives us Ni2, CO3 2, that we can in turn simplify to a 1-to-1 ratio. You only simplify your ratio of ions. For tetra, tetra tells us we have 4 associated water molecules, and that gives us the following chemical formula.
Is that a typo? 032?
No, it's not a typo. This is just our first draft. And then we simplify our ratio of ions, and that gives us our final formula.
Oh, okay, thank you.
Does that make sense? Just to
Yes.
just to show where we get the 1-to-1 ratio from. Any other questions on this example? Okay, let's keep going. And let's now focus on, again, naming the following compounds. So let's work on these next 2 examples, and let's try to name these 2 compounds, and we'll discuss this example in about 3 to 4 minutes. Practice really does make perfect for nomenclature, and the more examples we can work on, the more effectively we can name a range of different compounds. And don't be shy to share your responses or questions that you have in the chat. And I'd be happy to answer any questions that you have. We'll discuss this example in about another 2 to 2.5 minutes.
Professor, the formula for acetate
Yeah,
is the same as C2H2O2. I mean C2H3O2 is
yes.
the same as what we have. Okay.
So acetate can be written in either of these two ways,
Okay.
both of which are valid. Mhm.
Okay, great.
Let's try to get a few more responses in the chat. I'd like to see a pool of responses from different students. And if you have a question on any of these problems, don't be shy to ask. I do keep tabs on the responses in the chat, and I use those responses to help structure and design my examples and feedback. And we'll discuss this example in another minute to a minute and a half. And one thing to keep in mind is that zinc is what's known as a fixed charge transition metal. So you may not necessarily have to specify the charge using a Roman numeral. Okay, so let's discuss this example. So first, we need to figure out the charge of each of our ions. So we reverse cross our charge, we get Fe2 plus and CH3CO2 minus. That matches the known charge for acetate. So we would name this compound as iron 2 acetate. And now because we have 4 associated water molecules, what prefix do we use for 4 water molecules? What prefix do we use for 4 water molecules? Tetra, exactly right. So we call this iron 2 acetate tetrahydrate. Does this first example make sense? Any questions on this first example? Let's look at this next problem. So we have zinc nitrate. So we know that we have zinc 2 plus and NO3 minus. Now for zinc, if I write the name for zinc, as zinc is a fixed charge transition metal, I don't have to specify the charge. I then write my name for the polyatomic ion, which is nitrate. And I have 6 water molecules, so I call this hexahydrate. So this would be zinc nitrate hexahydrate. Does this make sense to everyone?
I'm sorry, can you explain that one more time?
So zinc is a fixed charge transition metal, so you do not need to specify the charge using a Roman numeral as part of the name.
Oh,
So
yeah.
we name our metal, which is zinc. Our polyatomic ion is nitrate. We have 6 water molecules, so we use the prefix hexa. It's a hydrate, so we end with hydrate. Does that make sense? Perfect. So let's try one last example, and I'd like you to write the formula for the following compound. And let's spend about another 1.5 to 2 minutes writing the formula for this following hydrate.
Professor,
Yes.
I'm sorry, I'm just logging on. I had a doctor's appointment, but when would this part of the lecture be up live on the?
It should be by tomorrow or Friday at the latest.
Okay, thank you.
Mhm. So let's work on this next example and let's try to write a valid formula given the name of the following hydrate. Hydrate naming problems are pretty useful as they both test the student's ability to name ionic compounds and they also test the student's ability to name hydrates. So it's almost like a 2-part question in a way. And we're starting to see a reasonable pool of responses in the chat, and we'll discuss in about another minute.
Professor, just for the review, for the fixed charge transitional metals, so
Yeah.
we have only zinc, cadmium, and silver, right? That's the only
Yep,
thing we
exactly right. Zinc forms zinc 2+, cadmium forms cadmium 2+, and silver forms silver plus.
And that's all 3. These 3 we need to know, right?
Yep.
Okay,
Mhm.
thanks.
Okay, so let's discuss this example. So samarium has the symbol SM as a 2+ charge from the 2. Iodide is a derivative of iodine. And as we know, iodine, a group 7A element, forms I-. So we cross our charges. That gives us SMI2 monohydrate. So we have 1 water molecule. And this is the complete formula for samarium iodide.
So we don't have to put the parentheses for the I.
No, you don't. Does that make sense? Is everyone comfortable with this example? Okay, let's keep going now and let's talk about our next subclass of compounds, which are binary acids. So a binary acid is a neutral compound containing exactly two different elements, one of which is hydrogen and the other of which is a non-metal, typically a group 6A or 7A element. So the state symbol is really important here. Pure binary acids are gases. So if you see the gas state symbol, we have to use the following naming convention. You write hydrogen, and then you write the stem of the second element and change the suffix to IDE. So if we're naming HCl gas, for example, we'd write our prefix of hydrogen. And then we take the stem of our non-metal, which is chlor, and then we change the ending to IDE. So this would be hydrogen chloride, which is describing HCl in the gas phase, okay? Now, binary acids are overwhelmingly and almost always handled as aqueous solutions in water. If we have the aqueous prefix, the naming convention changes. Aqueous binary acids have a different set of rules. So first, we write a prefix, hydro. You write the stem of the second element, and this time you change the suffix to IC rather than IDE. Finally, you add the word acid to the end of the name. So let's look at an example of this. So HCl aqueous would be named as follows. So we'd write the prefix hydro, we'd write the stem, which is chlor, and then we'd change the ending to IC, and then we'd write acid at the end of the name. So this would be hydrochloric acid. Does this make sense to everyone so far? So as a shortcut, IDE is for the gas phase, IC is for dissolved in water. So just be really careful with that. This often catches students off guard. You need to pay attention to the state symbol. Any questions, any parts I can elaborate on further?
Professor, could you go up a little bit? I want to see what the HClG, like a hydrogen chloride. Okay.
Yep, exactly. You write the prefix of hydrogen, you write the stem, and then you change the ending to IDE.
All right, thank you.
Perfect. So let's keep going now, and let's try, oops, one moment. Let's try to name the following compounds. So I'll do the first one, you'll do the second one. So HF, I notice it's in the aqueous phase, so I add my prefix of hydro. Fluorine is fluor as the stem. I then change the ending to IC, so this would be hydrofluoric, and as it is an acid, I write the ending of acid. So this would be hydrofluoric acid. If we wanted to name HF in the gas phase, we'd name it as hydrogen fluoride. So the state symbol has a pretty dramatic effect on how we name different binary acids. Does this make sense to everyone?
Professor, even we don't add the prefix acid in the gaseous state, are they still acids?
Yes.
Okay. Like HFG is still acid, right?
Yes. It's
Okay.
still an acid, but you don't put acid at the end of the name.
Okay, got it.
Any other questions? So let's now work on naming the following compound, and let's spend about 1.5 to 2 minutes naming the following compound. And remember, you don't have to put a prefix for the number of hydrogen atoms because this is a binary acid. Yep, exactly right. So let's keep working on this example. Let's try to get a few more responses, and we'll discuss in about another minute. Okay, so let's discuss. So we have H2S in the gas phase. So we use the prefix of hydrogen rather than hydro. And then we take the stem for sulfur, which is sulf, and then we change the ending to IDE. So H2S in the gas phase would be hydrogen sulfide. Comparatively, if we're naming aqueous H2S, we would call this hydrosulfuric acid. Do these examples make sense to everyone? Is everyone comfortable so far? Okay, let's try to do some examples where we write the formula from the name. So we have hydrobromic acid. So bromic is derived from bromine. So we have H plus for our hydro component. Bromine or bromic is Br minus in the case of acid nomenclature. We cross our charges and that gives us HBr, and we name this with an aqueous symbol as we have the prefix hydro and acid. Does this idea make sense? Does this idea make sense for writing the formula? Okay, so let's try to work on some examples, and I'd like you to tackle the following 3 examples, write the name for the following 2 compounds, and then I would like you to write the formula for this last name. And we'll discuss this example in about another 4 minutes. And we're starting to see some proposed responses in the chat. Let's try to get a few more responses and keep working through these 3 examples, and we'll discuss in about another 3 minutes.
Professor, when we are writing the name, we adding the prefix hydro. It should be one word, like it should be hydrosulfate or hydro space sulfate.
Yes, it's a prefix rather than a separate word. Well, hydrogen is a separate word.
But
Does
if
that
it's
address
hydro-
your question?
But if it's hydro, it's same.
Yes, it's a prefix that modifies. So you'd say like hydrochloric rather than hydrogen then chloride.
Got it. Thank you.
Perfect. And we'll discuss this example in about 2 minutes. And we'll discuss this example in about another minute. Let's try to get a few more responses in the chat. But the responses I'm seeing so far look good. They even have the right state symbols, which is great to see. Okay, so for H2S, we see the aqueous symbol, so we need to use the hydro prefix. Sulfur, we use the prefix, the stem of sulfur, then we change the ending to IC. So this is hydrosulfuric acid. For HI, again, we use the hydro prefix. I, we use the prefix of iode. and then we change the ending to IC, so it's hydroiodic, and then we end the name with acid. So for H2S gas, we'd name this as hydrogen sulfide, just as a bonus for comparison. And HI in the gas phase, we'd name as hydrogen iodide. So the state symbol is critically important to properly naming different compounds. Does that make sense to everyone so far? Is everyone comfortable with these examples so far? Everyone's doing quite well on these nomenclature problems after you've seen the rules for naming different types of compounds. Okay, let's look at this next case where we have hydrogen selenide. So selenide is derived from selenium, which is a 6A element, which has a preferred charge of 2-. So we take H plus, selenium 2-, we cross our charges, we get H2Se, and because our ending is IDE and we have a prefix of hydrogen, this is the gas phase compound. Does that make sense to everyone? Okay, so let's talk about another subclass of compound. In this case, these are our polyatomic acids. So polyatomic acids are compounds containing, as their name implies, hydrogen and a polyatomic ion. Now, oxyacids are a common variant of polyatomic acids in that they're acids containing hydrogen, oxygen, and one other element. So let's look at an example where we have H2SO4 aqueous, and let's try to name this polyatomic acid. So we'll look at two examples, H2SO4 and HNO2 aqueous. So the first step in both of these cases, is to write the name of our polyatomic ion. SO4 2- is sulfate, while NO2- is nitrite. Everyone following with me so far? Okay, so next we change the ending of our polyatomic ion to OUS if the polyatomic ion name ends in ITE. So NO2, we change nitrite to nitrous. As a corollary to this, SO4 2-, which is sulfate, we replace the ending with IC if the polyatomic ion name ends in ATE. So sulfate, this is a bit of an exception, turns into sulfuric. So you replace the ATE ending with IC. Does that make sense to everyone? Okay, so now just to finish off this example, you write acid at the end of the name. So H2SO4 would be written as sulfuric acid, while HNO2 would be written as nitrous acid. As another example, HNO3, we go from nitrate to nitric acid. So we call HNO3 nitric acid. This is why you need to know the names of your polyatomic ions as well. So you can name your polyatomic acids and your oxyacids. Does that make sense? Let's look at some special cases. So sulfate turns into sulfuric, phosphate turns into phosphoric. These are just some exceptions that you need to know and just be aware of. Okay, so let's now focus on naming the following compounds. Let's focus on naming the following compounds. So I'll do the first one, you'll do this next two. So H2SO3. So SO3 2 minus is known as sulfite. Sulfite turns into sulfurous. So we name this as sulfurous acid. So ITE replaced with OUS. Does that example make sense?
Professor, could you scroll up a little bit for a second?
Yes.
Thank you.
Does that make sense? Any questions I can elaborate on this?
Okay, thank you. I'm done.
Okay, perfect. So what I'd like you to do now is to try to name the following two compounds, and we'll give everyone about 3 minutes to work through these examples, and then we'll discuss. And if you have any questions working through these examples, don't be shy to ask them in the chat or verbally.
Professor, so on the H2, we don't have to put the hydro?
You don't have to put the hydro prefix because it is a polyatomic acid and that uses different naming conventions.
Okay, got it. Thank you.
Mhm. So let's keep working on this example. I'd like to see a reasonable pool of responses in the chat, and then we'll discuss. Are there any questions that I can address for any of these problems? Don't be shy to unmute and ask your questions verbally or in the chat, and we'll discuss these examples in about another minute and a half. Let's try to get a few more responses in the chat before we discuss. And if you have any questions on these naming conventions, don't be shy to ask. Practice really does make perfect when applying these rules. Yes, you had a question?
Yes, when we are writing the formula, why we put in, like, for example, on the first one, we put the hydrogen at the end, And then the second one, we put the hydrogen at the beginning.
So for most oxyacids, you put the hydrogen at the beginning of the formula. The formula of acetic acid is trying to convey the connectivity of the atoms. So if you went and drew a Lewis structure for acetic acid, this formula tells you a lot of information about how the atoms are connected together. So that's why the hydrogen's at the end.
So when we are writing the formula, it doesn't matter if you put the hydrogen at the end or at the beginning.
In general, for oxyacids, it's placed at the beginning.
At the, okay.
Yeah. Okay, so let's discuss these examples. So CH3CO2H, this is derived from the base polyatomic ion of acetate. The ATE ending is changed to acetic acid. So we change ATE to IC, and that gives us acetic acid. Likewise, ClO4 is known as chlorate, and chlorate is changed, not chlorate, perchlorate. And the ATE ending, once again, is changed to IC. So perchlorate turns into perchloric acid. Do these examples make sense?
Professor, on the acetate, is that the CO2H on the polyatomics or?
Acetate is CH3CO2 minus, otherwise written as C2H3O2 minus. So this is known as acetate. And from the base name acetate, for the polyatomic acid, you change the ending from ATE to IC. Does that make sense?
Yeah, but my question is this a on the polyatomic chart that we have?
Yeah, it is. It is.
Okay, thank you.
Perfect. Any other questions that I can address? So we've written out some formulas. Let's now try to apply what we've learned, and let's try to name the following oxyacids. I'll do the first one and you'll tackle the next one. So HBRO. So BRO minus is known as hypobromite. That in turn is converted. The ITE ending is replaced with OUS, and we have hypobromous acid. Does this make sense to everyone? Does this example make sense? Is there something I can clarify about this example? So let's now apply this skill, and I'd like you to name the following two polyatomic acids, and we'll spend about 3 minutes naming these polyatomic acids. And don't be shy to propose the name for these acids in the chat, or to ask any questions that you have in the chat or verbally, and I'd be happy to address your questions. Let's try to get a reasonable pool of student responses in the chat, and then we'll discuss momentarily. And if you have any questions in naming these polyatomic acids, don't be shy to ask a question as well if you're unsure. And we'll discuss this example in about another minute and a half. Okay, so let's look at our base polyatomic ion. C2O4 2- is known as oxalate. ATE is replaced with IC, so oxalate turns into oxalic acid. Likewise, Cr2O7 2- is known as dichromate. And dichromate in turn turns into dichromic. ATE turns into IC, so this turns into dichromic acid. Does this make sense to everyone? Any questions on these examples? Any questions on these examples?
Professor, can we do one more practice ending with ITE?
Sure. So to help us with that, I have a few follow-up examples, but if we want to write a name, I can give everyone a bonus example just so that way we have a little bit more practice. So I'd like you to write the name for HClO2. So this is an example that's added to the notes. So I'd like everyone to try to name HClO2 as requested, just so that way we can have more practice. So how would we name HClO2? Let's try to get some proposals for the name of HClO2, either in the chat or verbally.
So Professor, it becomes, I don't know if it's correct, chlorous acid? That's
Could you repeat that?
chlorous acid?
Yep. In other words, chlorous acid, because ClO2- is known as chlorite, and we replace ITE with OUS. Remember, the hydro prefix is only used for binary acids. Does that make sense?
Yes, thank you.
Perfect. So let's now try to write the formula given the following names. So I'll do the first two and you'll do the second two. So chlorus, the OUS is derived from ITE. I know chlorite is ClO2-. As it's an acid, I write H+ and my polyatomic ion and then I cross the charges, and that gives us HClO2 for chlorous acid. This first example is sort of a mirror of the bonus example we just did. A little bit more interestingly, carbonic acid, IC is derived from ATE, so carbonic acid is derived from carbonate. Carbonate is CO3 2 minus. So now we cross our charges. So we have H plus and CO3 2 minus, and that in turn gives us H2CO3. Do these examples make sense to everyone? Is everyone comfortable with these examples so far? Any questions so far? Okay, so let's try to apply what we've learned, and I'd like you to write the formulas for the following three names. So let's spend about 3 to 4 minutes on these examples, and let's try to write the formulas for each of these names. So let's try to get some proposed formulas for each of these three names in the chat, and then we'll discuss in about another 3 minutes. Let's try to get a reasonable pool of responses before we discuss. And if you have any questions on nomenclature associated with polyatomic acids, don't be shy to ask.
Real quick, us, we translate that to ide. When
OUS is translated into ITE.
ITE. Okay, thank you.
So we're starting to get a reasonable pool of responses in the chat. Just make sure that your polyatomic ion formulas are correct with the correct subscripts. Let's keep working through this example. It's good that we're seeing a reasonable amount of class participation, and we'll discuss this example in another minute to 1.5 minutes. And we'll discuss this example momentarily. Yes. So technically, because these nomenclature rules apply to aqueous oxyacids, you should put the aqueous symbol at the end of the formula. That's exactly right, and it's important to note that. So let's discuss. So nitrous acid is derived from nitrite, which is NO2 minus. So we have H plus and NO2 minus. We cross our charges, and that gives us HNO2. Phosphorus acid is derived from phosphite, which is PO3, 3 minus. So we have H plus and PO3, 3 minus. We cross our charges, and that gives us H3PO3. And we should have aqueous symbols at the end of each of our proposed formulas. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay. Permanganic acid, IC, replaces ATE. So permanganic acid is a derivative of permanganate, which is MnO4 minus. Now that we have each of our component ions, all we have to do is cross the charges, and that gives us HMnO4 aqueous. Does this make sense?
Professor, quick question. So
Yep.
on all acids, the hydrogen will be in the front?
Yes, in the majority of cases, yes.
Okay, thank you.
Any other question on these examples? If not, let's keep going now and let's talk about the last class of compound that we have to discuss, which are binary covalent compounds.
Professor,
So-
before we go further, sorry, I have a question. Why there is a 3? The permanganate is MnO4 minus only, no?
Yes, so what is your question? Sorry.
The question is why, could you go up a little bit? You put H3.
For phosphorus, yes.
Oh, okay, got it. Okay, I saw it wrong. Okay, thank you.
Did that
Yes,
yes. Clarify?
Yes.
So because phosphite has a 3 minus charge, we need 3 hydrogens in the formula to balance it out. Permanganate only has a -1 charge, so we only need 1 hydrogen.
Got it. Thank you.
Perfect. So let's now discuss the next class of compounds, which are binary covalent compounds. They have exactly 2 different elements covalently bonded. And these binary covalent compounds are typically composed of 2 different non-metal elements. So an example would be nitrogen dioxide, carbon monoxide, disulfur trioxide, the list goes on. So let's talk about the naming rules. Let's talk about the naming rules. So you write the name of the first element in the formula and you add a prefix if there are 2 or more atoms of that element. Then you write the name of the second element and you always add the prefix to the second element. Finally, just like before, when we dealt with ionic compounds, you change the ending of the second element to IDE. So here are the prefixes that you'll need to be familiar with. They're exactly the same as our hydrate prefixes, so that's a welcome sight to many of us, because it certainly makes our lives a little bit easier. Okay, so these are the rules. Let's show how these rules are applied in practice. So let's name the following compounds. So for PCl5, we write the name of our first element. So in this case, phosphorus. It's the first element in the formula. You do not need a prefix for the first element if there's only one of it. Next, we write a prefix for our second element. So 5 corresponds to the prefix of penta. Chlorine, we write the stem of chlor, and then we change our ending to IDE. So PCl5 would be phosphorus pentachloride. So let's try to work on these examples. And as a bonus, let's try to name S2Cl6. And before I let you loose on these examples, I'd want to show you an example where we have both of our elements with more than one atom. So let's look at N2O4, for example. So we'd write a prefix for our first element since there are two of them. So we write this as dinitrogen. We have 4 oxygens, so we have tetra. And then oxygen turns into oxide. So N2O4 would be dinitrogen tetroxide. Do these representative examples make sense to everyone? Do these representative examples make sense? So I'd like you to work on these 3 examples and we'll discuss naming the following binary covalent compounds in about 3 to 4 minutes. And we'll discuss this example in about another 3 minutes. And let's try to get a reasonable pool of responses before we discuss. And let's try to get a few more responses before we discuss in about another 2 minutes. And if you have any questions naming these compounds, don't be shy to ask. And I would highly suggest submitting your proposed responses and proposed names for each of these compounds. As it allows me to structure my feedback and address common student mistakes. And we'll discuss in about another minute. Okay, so let's look at this case. So we have one carbon, so we just write the name of our first element, which is carbon. For bromine, we have 4 bromines, so we write the prefix of tetra, and then we change the ending of bromine from bromine to bromide. So CBr4 would be carbon tetrabromide. Does that make sense to everyone? Does this make sense? Perfect. Okay, so looking at NO2, we name our first element, which is nitrogen. We have 2 oxygens, so we name it as nitrogen dioxide. Does this second example make sense? Okay, so looking at S2Cl6, we write a prefix because we have 2 of our first elements. So we write this as disulfur. We have 6 chlorine, so we name this as hexachloride. Any questions on these 3 naming examples?
Professor, on an exam, will you tell us exactly to name like binary covalent compounds or?
No, you'll have to know how to classify the compounds in order to effectively name them. And that's
Okay.
a very good point to bring up. So you'll have to be able to identify that this is a binary covalent compound, and as such, it needs to be named appropriately. Does that make sense?
Yes.
Perfect.
Yeah, okay.
Remember, binary covalent compounds contain exactly 2 different nonmetals.
Okay, yeah, got it.
Perfect. So let's try to name the following compounds. I'll do the first example, you'll do the rest. So we have 2 sulfurs, so we name this as disulfur. We have 2 chlorines, so we name this as disulfur dichloride. Let's work on these next 2 over the next 3 minutes, and let's try to propose names for these 2 compounds in the chat. Practice makes perfect. And if you have any questions naming these binary covalent compounds, I'll be happy to answer your question. And let's try to get a few more responses in the chat before we discuss in about another minute and a half. and we'll discuss this example momentarily. It's great to see a nice pool of responses from a range of different students in this class. So let's discuss now, since I see a lot of reasonable responses. So N2O, we have dinitrogen, because we have 2 nitrogen atoms. We have 1 oxygen, so we use the prefix mono. So this would be dinitrogen monoxide. Does that make sense to everyone?
Professor, when is only one, should we say mono or we can just say oxide?
You have to use the mono prefix.
Okay, thank you.
Mhm. For P2O5, we use the prefix of di for phosphorus. So we have diphosphorus. And we have 5 oxygens, so we use the prefix of pentaoxide. But when you're naming oxides, you avoid repeat vowels. So the correct name for this compound would be diphosphorus pentoxide. For essentially, when naming oxides, you avoid having repeating vowels. Does that make sense to everyone? Do these examples make sense? Okay, let's keep going and let's try to provide a formula for the following names. I'll do the first 2, you'll do the next 2. So dinitrogen tetroxide. Di tells me to write 2. Tetra tells me to write 4. Nitrogen, oxide, oxygen. Perfect. Does this first example make sense? It's pretty easy to write the formula of covalent compounds. It almost gives you a step-by-step guide.
Is a tetra like a leg of A there?
That's correct, because for oxides, so rather than saying like tetraoxide, it's common convention to replace these repeat vowels with just a single vowel.
Okay, got it.
Yeah, but like for everything else, you write out the full tetra. So like tetrachloride is pretty common. And that's a great lead into this next example, carbon tetrahydride. We have 4 hydrogens and 1 carbon. So we write this as CH4. Does that make sense? It's just a small naming quirk specific to oxygen. Do these examples make sense to everyone so far? Okay, so I'd like you now to provide a formula for the following compound names. And let's spend about 2 to 3 minutes on this example, and then we'll discuss. And if you have any questions writing the formulas for these for these binary covalent compounds, please don't be shy to ask any questions in the chat. And let's try to get a few more responses before we discuss in about another minute.
Professor, can you scroll down for a second?
Down?
Up.
Up? Okay.
Yeah, right there. Thank you.
May I scroll down now?
Yes, thank you.
Perfect. So let's keep working on these examples and we'll discuss in about another 30 seconds. So for nitrogen triiodide, we write out our nitrogen. We have just one because there's no prefix. Triiodide, iodide, iodine. Tri tells us we have 3 iodine atoms. Does that make sense to everyone? For sulfur hexafluoride, we write out sulfur. Hexa tells us we have 6. Fluoride derived from fluorine. So our full formula would be SF6. Do these examples make sense to everyone so far? Any questions?
Professor, I have a quick question. When we are using these prefixes, is when you're asking us to put the binary covalents in the formulas? Is that correct?
So the prefixes are used for binary covalent compounds. Does that answer your question?
Yes, thank you.
Perfect. So what we're going to do as we're at the end of the scheduled class session is that I'd like you over the weekend to practice and review the nomenclature rules. We will finish up chapter 3 next class session, and we'll go over mixed nomenclature. We'll do a lot of examples on mixed nomenclature, and then we'll finish up with an introduction to organic nomenclature. But what I'd like you to do now is during the weekend, I want you to prepare and review the nomenclature rules. You want to keep them current, because if you start to forget the nomenclature rules, you'll end up mixing them up when you start to deal with mixed nomenclature, where you have to both classify and then name a compound. So that's the end of today's scheduled lecture session.